Okay, so last time we talked about the two simplified ways to calculate changes in entropy. So for incompressible materials, from the TDS equations, we got that delta lowercase s is equal to C times the natural log of temperature 2 over temperature 1. And this is, we derived this from the TDS equations. And then for ideal gases, we got that. I don't have that in front of me. Oh, here I do. So yeah, so there are three equations we have. The two that where you don't need any kind of table information. So that's delta lowercase s is equal to Cp times the natural log of T2 over T1. Minus R natural log of P2 over P1. And then you have delta S is equal to Cv times the natural log of T2 over T1 plus R times the natural log of specific volume V2 over V1. And then more accurate, so these are for, small changes in temperature. So more accurate, but requires a table, is delta S is equal to S0 at T2 minus S0 at T1 minus R times the natural log of P2 over P1. So the only thing that's different is that this S0 thing gives you a more accurate calculation of Cp natural log of T2 over T1.
But then, so you need to have all the information though to get that.
Right? Yes, right. It's not like you can do it with less information or anything. It's just more accurate.
Oh, the other ones you still need.
You need all the same stuff, but this one, if you have a table, is more accurate. That's all.
Oh, okay.
And all of this is also from.
Oh yeah, because you need temperature and pressure.
Yeah.
Yeah.
And so, notice that the first one for small temperature is the same thing as this. The only difference was when we did the integral, like we got this first small delta T equation by assuming Cp was constant, so we could do the integral by hand. This does the integral including the changes in Cp over temperature range. Okay. Okay, so now what we're going to do, we're going to use these and show the direction that processes occur. So now we're going to use these calculations for delta S to show that processes can only move in one direction And we're going to do that using the entropy form of the second law. And that says that for an isolated system, or in an isolated system, the change in extensive entropy is greater than or equal to 0. Okay, so first, we'll do it with incompressible materials. So let's say that we have an isolated system, and by that I mean, so an isolated system means it's insulated, so there's no heat transfer. There's no volume change. And so there's no work of expansion, and there's no power, no electric power, rotating shafts going in or out. So there's no way to transfer energy across the boundary. And let's say we have 0.5 kilograms of steel that's initially at 400 Kelvin. And 10 kilograms of water, liquid water, that's initially at 283 Kelvin. And we combine these two things in this insulated container, and we have two questions. We want to calculate the equilibrium temperature of the system. And then second, we're going to use the entropy form of the second law to show that this can only happen in one direction. Okay, there's no way to go from being the same temperature to the temperatures diverging, So we're going to show the direction of the process. Or not show, but determine. Well, obviously everybody, including probably 5-year-old kids, would know that the direction has to be towards these things being in equilibrium. But here we can do that calculation. Okay, so we're going to use the fact that, so we're going to assume these are incompressible. And for incompressible, we know that C is equal to d little u dt. And so du is equal to c dt. And so the change in specific internal energy is equal to C times the change in temperature. Okay. And since there's no energy transfer in or out, the first law says that the change in internal energy is equal to Q minus W. These are both 0. And so we know that the change in total internal energy has to be equal to 0. Okay. Well, we have a way to calculate for each one of these materials the change in specific internal energy, which means that the change in extensive internal energy is just the mass times the specific heat times the change in temperature. And so now we can do these calculations. We only have 2 materials that add up to the total internal energy. So we have the mass of the steel times the specific heat of the steel that we can just Google or look up. I guess let me write this over here. So C for the steel is equal to 460 joules per kilogram Kelvin. And C for water.
Is that from our tables? Or
I think you can find that in the page that's just like different values for, but like on a test or something, I would just give you that value and you can just Google it and it'll pop up. And for water, it's about 4186. And so what this says, by the way, is it takes a lot more change in energy to raise the temperature of water than it does to raise the temperature of steel. Yeah, that's a lot. Okay, so we got 0.5 times the specific heat of steel times the change in temperature. So we're trying to figure out the equilibrium temperature. So I'm going to call that equilibrium temperature T2. And the steel is starting at a temperature of, what did I say, 400?
yeah.
Mm-hmm.
So we're just doing all this in Kelvin. This is going to give us our temperatures in Kelvin. Okay, that's the change in internal energy for the steel, and we want to add that to the change in internal energy for the liquid water. So that's 10 kilograms times 4186 times the change in temperature, which is the same T2. Remember, we're looking for these to come to equilibrium. So T2 minus 283. And these have to come out to be equal to 0. And so now just solve this for T2, and you get the T2 is equal to 283.6 Kelvin.
It's just that easy.
Well, yeah, I mean,
It's easy math, but getting through all of the.
yeah, right.
Yeah. Oh man.
Does anyone want to go through the algebra? I mean, no. Okay, so, well, since since that difference in temperature, that difference, like we basically end up at the temperature of the water. We're so close to the starting temperature of the water. There's a lot more of it, and water, a change in the temperature of the water reveals so much more internal energy hidden underneath, and that's why we have this small change. But now what we're going to do, so okay, if you threw this hot steel into this cool water in a Yeti cooler, and I get paid by Yeti to say, I get 46 cents for saying that every semester. Then, and you come back in a couple hours, this would be the temperature of everything. Okay, but now the thing is, there's no way to know from the first law whether these two things would start at 283.6 and move to 400 and 283, or whether they would do what I said every kindergarten kid would know, start at different temperatures and come to the same temperature. So now we're going to try putting this into the second law, the entropy statement of the second law. And so the entropy statement of the second law says that since this system is isolated, the change in entropy of the steel plus the change in entropy of the water has to be greater than or equal to 0. The change in extensive entropy is just the mass times the change in intensive entropy. And so we have 0.5 times the specific heat of the steel, 460, times the natural log of the later temperature, 283.6, divided by the earlier temperature of the steel, which is 400. So what we're calculating here is the change in extensive entropy, plus the mass of the water times the specific heat of the water, 4186, times the natural log of the final temperature, 283.6, divided by 283. And if you calculate this, you get that the change in entropy is equal to positive 9.56 joules per Kelvin. So this one is possible.
So then the way to check would you just flip it?
Yeah, right. I'm going to write that down, but exactly, you would just so this is possible. This is the one that's going from different temperatures to the same final temperature. So now let's try going from the same temperature to different temperatures. So this time we have that the change in extensive entropy is equal to 0.5 times 460 times the natural log of, so this time the later temperature would be 400. The earlier temperature would be 283.6. And then we're adding that to 10 times 4186 times the natural log of 283 divided by 283.6. And the natural log of a reciprocal is just the negative. And so this comes out to be negative 9.56 joules per Kelvin. And so this is not possible. Cool, right?
Super.
And I mean, you can't do the calculation, but intuitively you can say, like, you can think like, well, this is like, think of the Clausius statement of the second law. You know, the Clausius statement, the simple statement of the second law that just says heat can only spontaneously transfer from high temperature to low temperature, tells you that this is how it's going to work. Energy is going to leave the steel for the cooler water until those temperatures match each other, right? But we don't have a way to calculate it, and not all systems are as intuitive to understand as this one. This gives us a way to determine the direction. Okay, so let's see one with ideal gases. Same idea. So let's say that we have a box with a little box inside that we can open. So the box inside is this thing. And so in this area, we have 2 kilograms of air. With a volume of 1.6 cubic meters at 20 degrees Celsius. And in this little enclosed box inside, we have 1 kilogram of air. With a volume of 0.4 cubic meters at 100 degrees Celsius. And so, you know, through some electric switch or whatever, we open that box and let these two gases, these two amounts of air mix, okay? So we're gonna open the small box.
What meters for?
That's the new kind of volume. Okay, open the small box. Let the two mix. And we're assuming that this is this big box is isolated from the surroundings. And we want to do the same things we did before. First, calculate the equilibrium temperature. And second, determine the direction that this would happen. This is a pretty small range of temperatures. So we're just going to use so this is a small temperature change. And we're given volumes instead of pressures. It's pretty easy to, I mean, if you have the temperatures and volumes, you can calculate the pressures using the ideal gas law. But since we're given volumes, we might as well use the equation that says delta S is equal to CV natural log of T2 over T1 plus R times the natural log of specific volume 2 over specific volume 1. First, we just have to do the energy stuff. So for part A, let's see. We know that CV is equal to du dt. So this part is going to be exactly the same as it was in the incompressible case. So the change in specific internal energy is equal to CV times the change in temperature. And the change in extensive internal energy then is just the mass times CV times the change in temperature. And since these are both air, we're going to use these values. CV is equal to 0.72 times 10 to the third. And R is equal to 287. These are in SI units. Okay, so the total change in extensive internal energy is the mass of the hotter, higher pressure air times 0.72 times 10 to the third. Times our final temperature minus our initial temperature, which is 100 degrees Celsius. Since we're using a difference in temperatures, we can use, we used Kelvin in the last example. We're using Celsius in this one. That's fine as long as that's a difference in temperatures. And then we're adding that to the change in internal energy for the bigger volume of lower temperature gas. That was 2 kilograms times 0.72 times 10 to the third times T2 minus 20. And since there's no energy transfer, this comes out to be equal to 0. So go through the calculation and you get that T2, that equilibrium temperature, is equal to 47 degrees Celsius.
So we didn't even need to do, oh, I guess we didn't, yeah, so we don't need the entropy for that part.
Right, to calculate the equilibrium, you're just using energy. That's right, in both of those cases. But what we haven't done yet is determine, whether the temperatures are converging or diverging, you know. So that's what we're going to do now. And that's where we're going to use entropy. So first, let's calculate it for, you know, the temperatures start different. And come to equilibrium, or come to the same temperature. And so our change in extensive entropy is the mass of the stuff that starts at a higher temperature times, and now we're going to use that change in entropy formula. So we have CV times the natural log of the equilibrium temperature divided by the starting temperature of the 1 kilogram of higher temperature gas. So that was 100. Oh, this, I made a mistake here. Now we're not doing differences in temperature anymore. So now we have to put this into Kelvin. Okay, so this is 320. Yeah, so this is 320 Kelvin. So natural log of 320 over 100 degrees Celsius is 373 Kelvin. And then we're adding to that R, so 287 times the natural log of do we have a way to do this volume?
Just be the volume divided by the mass?
I guess that's true, yeah. So
Yeah, volume, right? Yeah, because
yeah,
because you multiply by the mass to get the what do you say, like intensive?
yeah,
Is that right?
yes.
Intensive is like the one that includes the mass.
Extensive is the one that includes the mass.
Okay.
So okay, so this is going to be V2 over the starting specific volume, which was, well, I'll just write that as V1 to start with. So now we have to calculate these volumes. So they're going to come to the same pressure. So we could calculate that equilibrium pressure at the equilibrium temperature and just use that. Or we could say, like you're thinking, the 1 kilogram of gas is going to take up 1/3 of the volume. And so the volume extensive is going to be
Oh, because you need to figure out the combined specific volume. Is that what you're getting at?
well, no, but we just need to figure out the volume that each one of those two gases takes up on its own.
Well, because yeah, I mean, if
once they're at the same pressure.
Oh, sure.
So there's a couple ways we could do it. We could we could calculate we could use the ideal gas law to calculate the pressure and just use the pressure formula, you know, and use the ideal gas law twice to find the starting pressure and ending pressure. Or we could use the fact that 1/3 of the total mass is going to take up 1/3 of the total volume. So this is, so V2, well, since they're going to be at the same temperature and pressure, they're going to be at the same specific volume.
So it would be 1/3 of 2 cubic meters, right? That's how much it would take up.
Okay, so hold on. So
So
so the total volume of the whole thing is the total volume is 2. And so the volume of the extensive volume of the high temperature gas I'll call that, oh boy, what am I going to call that? Of the high temperature gas is going to be 1/3 of this. So that's 0.6 repeating meters cubed. And there is 1 kilogram of this. So let me change this notation again. Sorry about all this. So the extensive V2 is this, which says that the intensive V2 is this because there's 1 kilogram of material. So this is for the one that's initially 100 degrees Celsius. And so we have delta S is equal to 1 times 0.72 times 10 to the third times the natural log of 320 over 373 plus 287 times the natural log of the final is 0.6 repeating. The starting is we had 0.4 cubic meters divided by 1 kilogram, so the starting is 0.4. Positive 36.26. This is joules per Kelvin. And now for the air that's initially at 20 degrees Celsius, the change in entropy is 2 times 0.72 times 10 to the third times the natural log of so
320 over 193.
293. Yep, right. 320 over 293 plus 287 times the natural log of, so now we have a specific volume of, well, it's going to be the same. Divided by our starting specific volume was 1.6 divided by 2, so this is 0.8. So we get 2 times and I got 22.28 joules per Kelvin. Okay, so does that match what I got before? Yeah. So the total change in entropy is 58.28 joules per Kelvin. And if we went the other direction, it would just be the reverse. This is positive, so this direction is possible. Going the other direction would switch the signs.
Interesting that they're both positive individually too.
It is interesting.
Like I would have thought that one of them would counteract the other.
Yes,
one.
me too. Yeah, that is odd to me too, but I guess it has something to do with the pressures. I mean,
so is that often what does happen? Is one of them is?
Yeah, often they offset. Like, yeah, I mean, because if you
like locally decrease.
Yeah, like in like a refrigeration cycle, you know, you're losing heat from the like you're losing heat from one part of the refrigerant, and so the entropy is going down in that part, and you're exchanging that for gaining more entropy somewhere else. I guess in this case, it just has to do with the interactions with the pressures. But okay, any questions about that? That was a little rough, but that's how it works. Okay, so what are we doing next time? So there's 2 more things that we have to do. So 2 more things to do with the second law. Those are talking about isentropic processes. And isentropic processes are processes where there's no heat exchange and no internal irreversibilities. And that's just an assumption that you can make sometimes, and when you can, it gives us a little bit of extra calculation power. And then the second thing we have to do is control volumes for the second law. So we'll get into that stuff next time. Okay, bye.